So let's get started here. We've been through the averaging concept. We've been through the way of closing the loop, designing the control. And today I'm going to wrap it up by the peak and average current mode, which are very important in providing better stability and better performance to PWM converters. And then finally, I'm going to talk a little bit about PID, which is sometimes used, and there is a confusion here, what it is and how is it related to what we are talking about. So I'm going to cover this one too. While talking about the peak and average current mode, I'm going to repeat the whole issue of average modeling, how to build the model, and how to do the control, so that perhaps it'll be better understood and visualized, and while talking about the current mode. Okay, so why do we need the current feedback? Why do we need? Well, obviously, in some cases, we like to control the current, but that's not the reason in many cases that we are using current feedback. The reason is that the system itself, the bare system of a PWM converter, due to the fact that it has an inductor and a capacitor, is a second order system. Therefore, inherently, it has a large phase shift, a large lag up to 180 degrees, because there are two poles there. And it is difficult to close the loop when you have that much lag. As I explained, the larger the lag, the more there is a tendency to instability, because you are going to encircle the -1 point. So the purpose of actually current feedback is to help in this respect. And I'll show you that what really happens in effect is that when you're adding a current feedback, you are like reducing the order of the system. That is, rather than having a second order system, you're going to have a first order system that is one pole. One pole has only 90-degree phase shift, and it's much, much easier to close the loop. So here is a general scheme of current feedback. We have, this is the buck converter, the switcher, the diode, inductor. Here we measure the current, translate it to a voltage, for example, by passing it through a resistor or some other means that will produce an output voltage proportional to the current. And then we compare this signal to a, I'll call it now a reference, because it's going to change, but let's assume it is like a reference. So we are comparing the two, producing an error signal, which is activating the modulator such that the error here will be reduced like in any feedback system. So it's a feedback system in which you measure the current, okay? So what really happens in effect is that you are controlling the current here. That is, if the feedback is strong, the loop gain is strong, high, there will be a good following of the current with the signal here. That is, if you change this signal to be a higher signal, the current will follow it. By that, one can understand that what is really happening is that you are losing the inductive effect of the inductor. It's now behaving like a current source, because it is following this signal, provided that you have a good feedback loop here. So if you have a current source, which is feeding an RNC, which is the load, this is the output capacitor, this is the load, this is the first order system. So this is the very basic explanation what really happens, that at the beginning, without this feedback, if you had here just a signal and modulator, you'll see a second order system. We've seen it in simulation. I'll show it again in a few minutes, actually. And then when you close the loop, because the current is following this signal, then it is reducing to this thing. So this is the main reason why we want current feedback. And there are many ways to do that. And that there's the peak current mode and average current mode. The peak current mode is more important. I'll, of course, talk about it in a few minutes. But before that, let's understand that we have the so-called inner loop, which is the current loop, measuring the current and forcing the current to follow this signal. But then this is not enough, because normally we want to stabilize the output. So therefore we have an outer loop here, output feedback loop, in which we compare the output to a voltage reference, or after a divider to a voltage reference, such that this output will be stabilized to whatever we want, okay? So we have the inner loop, and again, the purpose is to simplify or reduce the order of the system. And then we have the outer loop. Obviously, we need here phase compensation, which I'm not showing, in order to stabilize it. And with the B, 1 over B, we'll talk about it later on. Okay. Now, the most common method that is used for the peak current mode is this scheme, which I believe was originated by Redl and Sokal. And in this scheme, the operation goes like that. We have a clock, and this clock is determining the frequency. There's a flip-flop here. Whenever we have this clock signal, the flip-flop is set, and the transistor is turned on. Now, the current, since the transistor is turned on, the current starts to build up. Because, say, for example, this is like a boost converter, so there'll be here V in, V here, the point of the transistor. So we have the voltage imposed on the inductor current going up. And once it hits this point, or this value, it will reset the gate of the transistor, reset the input here to the driver, so that it's not as if you are providing a duty cycle, but the duty cycle is generated such that always the current will, when reaching the peak of the current, when reaching this voltage here, it'll end the duty cycle, okay? So it's a different scheme of modulation. It's not like a triangular wave comparing it to the voltage, but it starts with the clock, setting the flip-flop. This will be the beginning of the pulse, and the end of the pulse is when the current is hitting this value. And here is an example, which I'm just showing it for the reference of a modern controller peak current mode. This is LT8301 of analog devices, actually linear technology originally. And you see that the current is measured here, so that when the transistor is on, the voltage is imposed on the primary, the current starts to build up, and then this is this comparator, this is the flip-flop, and once it hits the value here of the reference that's coming from this side, this is measuring actually the voltage, then it'll reset, and this will be the end of the switch. By the way, this particular unit is working with the so-called primary side control. It's very tricky. rather than measuring the voltage at the output to stabilize it, it is measuring the voltage at the primary, the reflected voltage, which turns out to be during the off time, and it's sensing it in a clever way so that you don't have to have a feedback from the isolated side, which is very nice. There is a video on that, a YouTube video that I have in my channel, which is explaining this primary side control. Obviously, we don't have enough time to go into it. So here is a scheme, typical scheme. This will be for a boost converter. This is the input, the inductor, the diode, the output. I'm not showing actually the load here. This is just a divider to bring the magnitude here, the value to the reference, okay? And we have then the inner loop here. Here's the clock, the flip-flop. And this is the comparator, comparing this voltage here to the small filter. I'll talk about it in a minute. Comparing the voltage here to the voltage here. And this is the reference. So what happens here? Suppose the output voltage is incorrect. Say, for the sake of explanation, voltage is too low. If the voltage is too low, then the output here will go higher. This will cause the inductor current to become larger because the peak value is increasing. And this will tend to increase the voltage here until it will get to the point that the voltage at this here, at this divider is equal to here, and this is when it will stabilize. Okay, so we have the outer loop and we have the inner loop. It's a rather complex system, and analyzing it analytically is not simple. Deriving all the relationship is not simple. And as you already seen, I'm not going to do that. We don't have the weeks to do that. We're going to show, I'm going to show how to get whatever we need for the practical design by whatever we need by simulation. Let me say that one problem that is encountered here is that when you have a signal coming here to the gate from the driver, when the clock is on, flip-flop is on, you get the pulse coming up through this capacitance gate to source, we get a disturbance here, which shows itself as a spike. Now, obviously, this could affect the operation because if the spike is high, it will be recognized as if there is a current already high and it'll reset. So therefore, we need either a filter to filter this thing, or in some cases, there is a blanking inside. That is, the controller is designed in such a way that it doesn't look at a certain period after the switch is on, sort of blanking it out and starting to sense only after that. This will be within the controller. Okay, so this is one of the few issues that one has to take into account. Now I'm showing here a digital implementation. And again, this is now a this is a buck converter, the switch. Now we are measuring the current here, because when the switch is on, this is when we are interested in the current. When the current in the inductor is building up, when the voltage here is high. And again, there is a comparator which is done in an analog way. The rest of it is digital. Why is it in analog? Because to do it in a digital way, you have to sample the current at very high sampling rate, because you have to hit the minute, the instant that it reaches the peak value. So if it's a 100 kilohertz switching, you have to sample it maybe at 1 megahertz or even higher to make sure you're not missing the peak. So rather than doing that, what they did here, they put a comparator, which is an analog one, and of course, there's no problem of resolution here, but you see that the reference to it here, this value here, okay, this one here, is coming from a digital to analog converter, and you see there is a blanking here, and this is a implementation, or a digital implementation of the control, which in this sequence of lecture, I'm not going into the digital control. So what is the advantage of the peak current mode? Aside from the fact that it is, as we will see, reducing the order of the system, simplifying control, it also provides as the so-called cycle-by-cycle protection. Because suppose there is a short and the current goes up very high, very fast. As the current will hit the maximum value here, which is equal to this one, the gate will turn off, so that you have a built-in protection cycle by cycle by the system itself. Like here, suppose there is a short, the transistor is on, the current is shooting up very fast, but it is sensed here. And when this current, this value hits this threshold, it'll turn off. So it's a built-in protection, and this is why one of the reasons why we like very much peak current mode. But there are many issues. I've mentioned one of them, the edge spike, but there is another issue, which is the subharmonic oscillation. And let me explain it here the way this was investigated first by Professor Middlebrook. Many consider him as one of the forefathers of power electronics from Caltech. And this is actually his explanation. I'm just giving the end result without doing all the geometry involved here, okay? So what is let me go back here, first of all. This is what happens when you have subharmonic oscillation. Rather than having a fine triangular waveform to the inductor, it starts oscillating like that. It's called subharmonic because the frequency is lower than the basic frequency. Usually oscillations are at resonant frequency or higher, but here it's lower. We have shown, there are many papers on the reason of this thing, etc. Aside from the simple explanation that I'll go over in a minute, there are many, many papers on that. We have also a paper showing that this is really a phenomena of what is called chaos. This is the chaos phenomena. You can show that it's getting into this regime of chaos, and this is why it's oscillating. Now, obviously, we don't want it. We just don't want it, okay? So this is one problem we have to be aware of. It has a solution, I'll talk about it, but this is a problem that you have to address when designing a system like that. So what is the explanation? And I'm, again, repeating the explanation of Professor Middlebrook, and that is the following. What I'm showing here is the inductor current, okay, of any PWM converter. At the on time, okay, here, the current starts to go up, and at the off time, the current goes down. This is very typical on any PWM unit, and we have seen the generic model of PWM is the same. Doesn't matter if it's buck, boost, or whatever. Now, suppose there is a disturbance in the current, noise, change of load, something. And this is the disturbance, and the current now starts going like that because it starts higher. This is the threshold at which the flip-flop will turn off. This is this point here, or this point here, okay? This is the threshold here. And once we hit the threshold, then it'll go down. This will be the off period. This is the threshold, and this is the on time. Now we are at the disturbance. So it's hitting it earlier, and then it goes here to the end of the period, and then they'll start a new cycle. The new cycle will start from here, okay? Suppose now that the duty cycle that you are working at, by the way, the ratio of the duty cycle to the input-output is the same here, because if you go into the system itself and just talk about the duty cycle that you have net here, how it affects the stage, it's the same thing. The question is, how do you generate the duty cycle? But once you have a duty cycle, V out to V in ratio, okay? So now starts a new duty cycle. Now, if the duty cycle you are working at is larger than 0.5, you'll have similar thing. With the disturbance, it goes up to here, and then it goes back here, and you start a new cycle. It can be shown by geometry, looking at the distances here with the triangles, etc., which is kind of long, but the end result is that if the duty cycle that you are working at is lower than 0.5, you end up with a disturbance which is smaller than the one you started with. You can see it pictorially here, but this is not a proof, of course. On the other hand, if you are at a duty cycle which is larger than 0.5, here it is, this is the duty cycle, and you have the same disturbance, you end up with a disturbance which is larger than the one you started. So this is obviously an unstable situation because, by the way, it's reversing the polarity. So here it's a positive, and now it's negative. Same thing here. This is why it's a subharmonic oscillation, because this is like one cycle, positive and negative, and then you have the second half cycle, so it will be half the frequency of the switching frequency. So the end result is that for duty cycle below 0.5, there's no problem. It will die out because this disturbance now is smaller than the beginning, then it'll be smaller and smaller, and that's the end of it. On the other hand, if it is more than 0.5, the duty cycle, then what will happen is that it'll start oscillating as it is shown here. Okay, this is from simulation of a system in a time domain which has a duty cycle larger than 0.5. So what can be done? What can be done? There are two things that can be done. One is to work always at duty cycle lower than 0.5. And in many cases, for example, flyback converters, this is done like that. You can do that. Or you can add what is called a slope compensation, which will remedy, again, due to the shortage of time, I cannot develop the proof of it, just give the end result. Whoever is interested, there are many papers, and the original paper of Professor Middleroth will gives all this. And what it is that we are adding to the current a slope, making it going up faster. We can add it to the current itself here. That is originally, this is what we see here. This is when the transistor is on. Now we are adding this thing, or we can add it to the VE, but of course in opposite direction because the difference should be the same, and so it would be a downslope. And it can be shown that if this addition of the slope is equal to S1 plus S2, S1 is the slope during the uptime, volt per second, and S2 is the slope of the inductor during the off time, which is not shown here. If the slope added here is equal to this plus this, then you will not, it is like pushing the operation from here back to here by making the slope faster, okay? So this is the solution that is adopted in many, many cases by adding the slope compensation, either externally or internally. For example, here, okay, you see this is an oscillator. The oscillator is built around a triangular waveform. So this triangular shape, or part of it during the on time, is added, or in this case subtracted, to this value so as to add this slope compensation as it is shown here, okay? So we are adding from the clock. The clock is being around a triangle. It's like charging a capacitor and discharging in. So during the charging, you have a slope, and you take this slope and you add it here in a reverse mode. So this is what is done here. So the question is, how can we handle the control of peak current mode? Okay. Now, in general, as we have said, the system that we have includes the power stage, which is invariant. It's the same thing. We have feedback. Now we have both voltage and current. Then we generate this VE, which is then going to the modulator and producing the duty cycle. So the question, how to model this thing? And again, you can take the expression of the transfer function, do small signal averaging, or some other means of getting the perturbation, small signal. You end up with many expressions that you have to add up. And we are going to leave this whole hard work to the simulator. And let's see what we're going to do. The concept that is very important to understand is that a PWM system with whatever type of control can be sort of displayed like this. We have the power system. This is this part here. And then we have a way that we are generating the rule for the current of the inductor. And this is by placing the average voltage across it. Then we have a block which I call duty cycle generator. It could be a simple PWM converter, or it could be a peak current mode. In order to simulate something like that in the average modeling that I'm showing here, all you need is the expression for this thing. You need the equation that relates these parameters, VE, the inductor current, and produces the duty cycle. It is an intricate mechanism that is doing it, but luckily, Professor Middlebrook, 1989, showed that this is actually the value of the duty cycle, that you can calculate it from all these parameters. What it is, this is the threshold, this is the inductor current, this is the translation of the inductor current into voltage, like this would be the resistance of the sense resistor, if you are measuring it with the resistor, that many milliohm that convert the current to a voltage, because everything here is in voltage, the units. This is the slope compensation, the period of the switching, the 0.5. This is again the same K. And this is the voltage, VAB, during the on time. Remember, in the switched inductor, during the on time, we have, when it is on, then you have this A and B, which is connected, which is one branch. Well, let me show it here, okay? A and B. I'll go talk about it in a minute. So once you have this, you can do either way. You can do small signal perturbation, get the transfer function, or you can leave it to the simulator in the AC analysis. That's exactly what the simulator is doing. Now, there are many papers that we have written on that, and I've brought here some of them, which explain everything in much, much more detail than I can do in these lectures. So whoever is interested is welcome to look at them. Obviously, you can at IEEE Express or even Google, just Google my name and P current mode, and you'll get all these papers. Okay, so let's get to it and see how we do this, first of all, simulation, and then the control. Okay, so here is the problem I'm showing. This is the buck converter. I put it the other side because I wanted also to apply it for the boost, but this is the input. These are the two transistors. I'm measuring the current. This is the control. Here is the inductor, output section, measuring it, everything, all action of translating all this information into a duty cycle is in here, and it is the Middlebrook equation. That's what's in here, because it needs all this information, okay? So I'm starting now to, first of all, build the average model of the switched inductor itself, okay? So we have seen that we have the basic generic unit. We can show, or we can express the average current ABC as here, where here are the expression. GD is B is the D on times the inductor current, and this is D off, and this is actually the inductor current. GA is the current here, okay? Going this way. And then we need to generate the average inductor current by imposing on the inductor the average voltage. Okay, so this is the very basic. So now we go to our case. We have the buck converter. I'm talking about the converter itself. This is A, this is B, and this is C. So now formally, these are the three sources, okay? And I think we have very bad connection. So once I sort of eliminate this because I'm connected to the inductor, I don't need this, and at this stage I don't want this one, then basically this boils to this simple circuit, because I've imposed the average voltage on the inductor, which on one side sees out and the other side sees D on times V in. And the inductor current is now feeding the output. I don't need for that a to emulate it with the current source, just translate it, I can just connect it, and that's it, okay? And we could have seen it directly here. If you look at this circuit, you understand that basically you have here an average voltage, which is in times V in times D on, and that's the end of it. Now, if you want, you can add this source with the current source, D on times IL, to emulate the current that goes into the source. I'm not doing it. Okay, so here it is. This is the stage itself. This is the output. This is the inductor. This is the D on times V in, and I'm assuming V in 50. I've just put in 50. So this is the thing itself. And then what I have is the compensator, which we'll talk about, which is producing the error signal. And this value plus some other information, let me go here, this value, some other information is put into the Middlebrook equation. This is the equation. Okay, this is this equation. Okay, this is just in the syntax of LT-SPICE, exactly as it is. Okay, so here it is. And I'm showing here just a run in the time domain to show the output and the inductor current, and to emphasize that we are in the average domain. We don't see ripples. Everything is smoothed out. The actual current you can get from LT-SPICE, but you certainly get it from PCM, which I understand you are more familiar with. This is a peak current mode implemented in PCM. And in this case, what you see the inductor current with a ripple and ripple at the output, which of course you don't see in the average model. Now, the beauty of this whole thing is that we can run small signal analysis. And as I've explained, the first step in the AC signal and the AC simulation is linearization of this equation and getting the small signal responses. And this will be correct for everything else in the circuit. Now, I've added here an excitation, AC excitation. And as I explained, this can be very useful to look at the loop gain, which I'm not going to do at this minute. I'll do it later on. But I like to emphasize that once you do an excitation anywhere, for example here, all the signals have AC components on them, okay? Everything is sort of breathing with an AC on it. So here, I'm going to see an AC component, and here, I'm going to see an AC component, and the ratio between here and here is the transfer function in open loop between duty cycle and the output. This is something we did the lecture before, okay? So it is closed loop now, but I can get partial transfer function from point to point because I have all these values here. So if I look from here to here, which is basically the stage itself, and by the way, this is the analytical expression for output to small duty cycle of a buck converter. What we see here, the second order denominator, polynomial, which means that it turns out to be imaginary, and it has two poles, of course. And we have a zero. The zero is due to this capacitor and this resistor, okay? There is a 0 here. And this is the analytical expression. Now, we're not doing this here. We are just hitting the button of AC analysis and getting it here. Okay, so this is this equation just plotted by the simulator without us doing the calculation. And what we see here is a second order system, and then we see here a 0. The phase supposed to go to minus 180 degrees, but then there is an advance due to the 0 of another 90 degrees, so it ends up at 90 degrees here. Very nice, excellent. Now, if this would have been the case of a voltage feedback, okay, voltage mode feedback, and I'd like to design a compensator using the method I've shown last meeting. I have this 1 over B. I can do it here because I have a rate of closure of minus 20 dB per decade. I can do it here, or perhaps I can do it here, again having this rate of closure. This will give me a very narrow bandwidth. This is the end of the bandwidth. This is better, but this is complex. The compensator is a type 3, 2-0, not simple, and also you have to check it for all operating points. So if you design it for one operating point, it may not be good for the other operating point. It's really difficult. This is not practical or not possible, because if the switching frequency is 100 kilohertz, you cannot close the loop above it. You have to close the loop at least 1.5, half of the switching frequency due to the Nyquist sampling criteria, and practically like 5 times lower or even 10 times lower. So you cannot do it here. If this would have been at a lower frequency, perhaps, but not in this case. So I'm showing the difficulty of closing the loop on a second order system. And this is why we want to add the feedback, the current feedback. And now I'm showing from the output of the error amplifier to the output, the whole thing, including this equation, because now I am including this equation in this path. This is AC here, there is AC here, so I can look at the ratio between here and here. This is the open loop response of the stage with the closed current mode feedback, current feedback. And here is what I am getting. You see, it's different. It goes down much slower, and the phase, you see, this is now 90 degrees, okay? It was earlier very 120, 160 here, and here it's low. I mean, the leg is much smaller, so it's more like a first order. Then we see the effect of the higher 0, which I'm not interested in. But I can see that I can very nicely close the loop here. This will be a type 2 compensator because it's straight here. And the phase here is 80, so that the phase margin is something like, I don't know, say 90 degrees or even more than that. That's very good. Excellent. Actually, we could have closed the loop a little bit further, but I have to worry about the switching frequency. This is a bit close. I might have gone actually lower because it's a bit close. Once you get close to the switching frequency, you have phenomena of sampling, and you can have oscillation, which are more in the digital or sampling domain, and you cannot explain them in a small signal transfer function, okay? So I'm going to close the loop here. And I'm going to do it by the type 2 or leg lead compensator, which looks like that. It has this transfer function. 1 over B is like this. And I'm going to use this part here, okay, to close the loop. And here is what I'm not showing how I calculated it, but this is the end result. This is the compensator. Here, it's beyond the amplifier response. That is, the amplifier has a finite bandwidth, and therefore the gain drops very much. So this is correct up to here, perhaps. This is due to the amplifier. So this is the compensator. And what I'm going to show is this is 1 over the compensator, 1 over B, and this is where I'm closing the loop. So this is the gain of the stage with current mode, and this is the compensator. And here is, well, the phase of each one we'll see in a minute. So this is the whole concept. That's it. Now, I can look at the ratio between here and here, and this will give me the loop gain, okay, as I explained last time. And here it is. This is the loop gain. This is the 0 dB crossover. This is the phase, 90 degrees, as we said, about 90 degrees. And we have a bandwidth of about 20 kilohertz. Beautiful. Okay. So, summarizing, we start with building the model of the stage itself, adding the current mode by the equation, and then we have to design the compensator of this system, which is of reduced order, as I've explained, which is much easier with the type 2 compensator. And here is the response of the system in the time domain to a 1 amp load, change of a load. You see it's going down about 80 millivolts, which is for 10 volt, it's pretty good. And it recovers in a, I guess it's 50 microsecond or something like that, which is also respectable. So before that, let me just say something about the compensator. The compensator has a reference here. This is coming from the 5-volt divider, 2.5 volt here, the 1-to-1. And then there's a gain between here. This is dropping the voltage to the 2.5, about 2.5, okay? And then we have the gain here. This is the resistor, this is the capacitor, this is the input resistor. I've put here a 10 meg to sort of limit the gain at very low frequencies, because at very low frequency, it's like an open circuit because the capacitance is like infinite impedance. So I've put here 10 megahertz, not necessary. It helps in the convergence. It's not operational because we are not using it, okay? So this is now the comp, and as I've added, this is just a clamp. Very simple. So now, as I've said, mentioned earlier, I guess, in LT-Spice, by right-clicking here, you can change the scale. Right-clicking here, you can change the scale to Nyquist. And this is the imaginary part axis. This is the real part axis. And this is frequency, starting from very low frequency to infinity. And there is, of course, the negative frequencies, which we don't see, of course, in the simulation. Now, what is important is what is happening here around the -10 point. And lo and behold, this is zooming up. This is the unit circle that I've explained. This is now the curve, this curve getting into it. And we see it's getting at 90 degrees, so the phase margin is indeed 90 degrees. Everything is fine and good. And if the encircling would have been like this, then of course, this would have been an unstable system. So this is what I can do with the peak current mode with the time allowed. And let me move to the average current mode. In the average current mode, the operation is different. We have an inner loop, but now the current is smoother. Now, obviously, we are losing the whole concept of cycle by cycle protection because it's just too slow, because we are smoothing it with the low pass filter. But on the other hand, we don't have the subharmonic oscillation, because the subharmonic oscillation has to do with the slopes and the interaction of the slope with the limit. So it has the advantage of not having the interaction or the subharmonic oscillation, but then you lose the cycle by cycle. And this is why this is not that popular, although it can be done. And some systems work like that, but it is a possibility. The concept, it's still reducing the order of the system. The compensator is accordingly simpler, but again, it loses some of the highlights of the peak current mode. So if we compare the voltage mode, which has second order system, minus 40 dB per decade, and perhaps a zero here, to the current mode, we see that what we gain in terms of the control is that the system becomes of a lower order, so therefore we can here close the loop, while here it's more difficult. It's not impossible, but as I've said, type 3 is not only difficult to design, and more complex, but also it's very, very sensitive to the operating point. And if you have a wide range of operation, you may have a good control at one point, and then you may lose it at another point. So this is very, very sensitive. Okay, so now I'm moving to PID. In power electronics, usually we do not use this term PID. We are just talking about type 1, type 2 controller, poles and zeros, etc. In many branches of technology, the chemistry industry and many others, where you have system with feedback, they are using the concept of PID. And what I'm trying to show here is the relationship between this concept and what we are used to do in power electronics. Now, let me just say that now that we are now using digital control, it's actually easy to use this concept of PID because it's easy to implement in a digital form because you have simple difference equations that you can describe them. So what is PID? Rather than having the compensator as we had it, like a function with a zeros and poles, we have three branches that we add up. This is the proportional branch, it's a constant. This is the integral branch, and this is the differential branch. So the PID, proportional, integral, and differential. So you get an output which is the sum of these. It's not a product, it's a sum. It's kind of different from what we are using. But you can add them up. Here I did it, okay? And just express them like this. And what do you see? you see that this block, which is used, as I've said, very widely in many, many branches of technology, many places, is nothing but this when expressed as one transfer function. It has two zeros, which with practical values here are real, two real zeros, and a poled zero that is an integral, okay? Now, the location of this zero is, of course, the solution of this second order equation. It's a double zero. Two zeros, which are real. Now, if you plot it, there are two ways to plot it. You can plot it as, sorry, doesn't go back. Okay. You can plot it like this. So you'll have a zero integral, so it'll go zero integral and zero. Or what I'm doing, I'm plotting each part by itself, okay? So the KP is this, the integral is this, and the derivative is this. Now, if we look at this frequency, this value is much lower than this one, so it's basically, or let's go in here already. So this value is much lower than this, so this is basically this value here. Here, this is much higher than everything else, so it's basically here, and here it's much higher than everything else. So this is the PID transfer function of the PID. Okay. So we understand that we have now a B, as I called it, a compensator, which has this waveform, this function. Okay? Now we are used, what I'm trying to show you, it's beneficial to look at 1 over B to understand how to use it and how to close the loop. And we see that 1 over the PID is something like that. This is 1 over. Okay, so now we understand the following. We can use it like this to close the loop here. We can use it like this, close the loop. Or we can use it as actually type 3 compensator. So you can say that the PID is kind of a general purpose compensator, and you can move it up or down, right or left, depending on the constants, okay? So by changing this constant, you are changing the places of the zero and the poles, and consequently, you can do this, you can do this, you can do this, okay? So you can do everything with this PID. So it's the same thing. It's just rather than looking at one particular configuration that you are interested in this case, for example, I am just interested in this. That's of my interest here. The cross-section, the straight line, the rate of closure here, and high gain here. Well, this is beneficial because it's reducing noise, actually, but I'm not, for the control, I'm not using it. So rather than just talking about this, I have the whole thing, and by choosing properly the constant, the K, I can move it around and close the loop. Now, this is not the way people in the chemistry industry are looking at it. I can tell you that the way they're doing it is kind of look archaic. They have three knobs in the system, and they are twiddling them, they're turning them And what they're doing is they are subjecting the system to a step response and looking at the response to a step. And then there are some rules how to turn this knob or this value up or down in order to get a good response. This is the way they're doing it. But in my approach, once you know the transfer function of the system, you know exactly what you need upon the way you decide to close the loop. So lo and behold, we are at the end of the last meeting here. This is just showing you the type 3, which I've mentioned. This is type 3. And as you can see, this is the PID, okay? This is the PID. And we are using this part here. Here it is in the type 3. This is 1 over, okay? So you see the resemblance. I'm leaving you with the problem. And that is the following. You know that in isolated converters, we need to have an isolation in the feedback because we have different grounds. We cannot have a common ground if we have an isolated. The whole purpose is to have isolation between the ground. And now I'm posing this question, where to put the isolation? Can we put it here? That is to do the comparison here, to put the compensator here and transfer it here, to do it here. That is to have everything here and just to get the PWM, or to do it here, or to do it here. So they are this way. And I think with the information that we went through in this, take a few minutes just to play a little bit with this LT5 here. That's on the one here. This is the circuit we just seen, okay? And it's already in the, here is the transient mode, okay? Now running. And by the way, I didn't mention it, I've put here a current source of 1 amp. It's a current source of 1 amp that is starting after 3 milliseconds, okay? And so it's sort of loading the unit. So I'm running it. And takes a little while. Okay, and well, this one I close actually. Here, I'll open it. And I'm going to look, how is this step affecting the output? How it is affecting the output of the compensator? And how it is affecting the actual duty cycle. Okay, and so this is what I've shown you before. This is how the output is affected. Now, since there is a drop in the output, we can see now how is the compensator responding. Okay. So the compensator output was 2.3, and since there is a slight change at the output, and there is a need for more current, this is actually the VE we talked about, okay? The VE was 2.37, and now it's going up to whatever, 2.64 to accommodate the higher current, okay? And then I can look at the actual duty cycle. And this is how the duty cycle changes. Now notice something very interesting. VE moved up because it is determining the peak current. And the current now needs to be higher because I've loaded it with an extra 1 amp. But the transfer ratio between input and output is the same because I'm keeping the same output and the same input. So the actual duty cycle should not change very little, only due to parasitics. So before and after the change, you see the duty cycle almost does not change. There is a disturbance here. It's trying to correct it very quickly by increasing the duty cycle, so to build up a higher current. But then when the current comes to its value, let me put the current now. Here is the current, average current. You see, we had this current, and now it went to a higher value. I've added 1 amp. Again, VE was related to this. VE now is related to this. The duty cycle does not change very much because the output is still the same output. We've seen that there is a small disturbance at the output, but then it's kept 10 volt also. So you can see all these very nice features and very accurate behavior in a comfortable way. Obviously, if you have a system, you can probe with the oscilloscope and some differential probes, etc. Look at current probe. But here you can do it very nice.